Hey, have you ever wondered what the voltage looks like on a dipole antenna? So here's a dipole antenna. So when antennas radiate, you connect them to some kind of generator, and this is AC generator. It's this alternating current, which means the current goes back and forth, back and forth, back and forth. And what ends up happening is the electrons go back and forth, back and forth, back and forth like that. They create a changing magnetic field that radiates out, and that changing magnetic field creates current in an antenna over there somewhere else, and that's how wireless communications happens. But why is an antenna a particular length? And does it make any difference? The answer is yes. So I want to talk about why an antenna is a particular length. So to understand that, we have to look at voltage over time. So when you talk about this generator right here, the voltage it generates, it ends up generating what's called the sinusoidal voltage. So after a certain amount of time, the voltage will become positive, it goes back to 0, becomes negative, back to 0, positive, back to 0, like that. And you know that this is one cycle, okay, or one wave. We can say one wavelength, kind of. Yeah. It'll travel one wavelength in the time it takes for one cycle to take place. So if this is one cycle, or one wavelength, that means from here to here is a quarter wavelength, and from here to here is another quarter, and from here to here, these are quarter wavelengths. That means from here to here is a half wavelength, right? From here to here is a quarter wavelength. So that's good to know. And then, if you look at this antenna, you know that the end of the antenna, the voltage is always a maximum. So if you looked at the voltage, it starts out maximum. If this antenna is a quarter wavelength long, then the voltage distribution is going to look like this. If it's a quarter wave long, from here to here. It also means that a half cycle later, the voltage is going to look like this. And then a half cycle later, the voltage will look like this. So the voltage will just keep going back and forth. Positive, negative, positive, negative, positive, negative, because the voltage that you're supplying to the antenna is positive, negative, positive, negative, positive, negative, like that. So what that means, if there was an electron here, this voltage is going to exert it's going to push the electron in one direction, and then a half cycle later, it'll push it back the other way, and a half cycle later pushes it back the other way. So in effect, the electrons are going up and down like that. So you need a constant voltage to make the electrons do that. So this works only if total length is a half a wavelength, right? So quarter wave on this side, quarter wave on that side, total length half wavelength. What if we imagine total length was a full wavelength? Let's see what would happen there. So draw the antenna. Full wavelength. So from here to here is a full wavelength. So remember, look up here. Full wavelength is, well, we know the end has a maximum voltage. So we can say the end might occur here. So from the end to this point, that's from here to here, that would be a half wavelength. So from here to here's a half wavelength. If we look at the voltage distribution, it would end up kind of like that. And here, same thing, right? Because if you have a positive voltage here, by the time you go half wavelength, you're into negative voltage. So what you end up having is you have positive here, negative here, positive here. So whatever the electron's doing in the presence of the positive, the electron in this side, in this part, is going to be doing the opposite. So if you look at the total radiation or fields generated by the current here, this and this is opposite and equal. They'll cancel each other out. Same thing here. No radiation. That's not good. So if the total length of the antenna was a full wavelength, it wouldn't actually radiate because these fields would cancel and so would these. But if we go back up here, if it's a quarter wavelength here and a quarter wavelength here, total length half wavelength, these are always the same. There will be radiation. To review, length total is a half wavelength. Radiation. If we go like this and say length is equal to lambda, no radiation. So there's a reason they call the half-wave dipole a half-wave dipole. Is because when it is most efficient, when it is radiating the highest percentage of power, the length, total length, is half-wave length, half-wave dipole. That is why.